Hi. In this video and the next I will explain and demonstrate my simulation in logisim of the TX-0 computer. In this video I will give a quick introduction to the TX-0 and then we'll talk about the data paths, and in the next video we'll look at the instruction set and the control section of the machine. So the TX-0 was built in the mid-1950s by Ken Olsen and Wes Clark, and it was one of the first transistorized computers. It was seminal in a number of ways, in that it was a stepping stone for the bigger TX2 computer built by Wes Clark, and best known for being the computer that ran Sketchpad, the first CAD program. But also Ken Olsen founded Digital Equipment Corporation after having built the TX-0, and DEC's first product line were the so-called lab modules and system modules that were essentially repackaged versions of the circuitry used by the TX-0. And DEC's first computer, the PDP-1, is a very direct descendant of the TX-0. The data path is very, very similar. And culturally, it's notable for being the computer that started the MIT hacker culture at the end of the 1950s. The TX-0 is an 18-bit computer with a 16-bit address space originally. So that means we have 64 kilowords of memory. As you can tell by that, this only leaves 2 bits for an instruction. So there are only 4 base instructions in the original configuration. But the machine was modified in a number of ways over the years, which I won't go much into, at least for now, maybe in the next video. So what I'm showing you here is the more or less original configuration of 1956 or so. And what you see here in logisim is the complete TX-0, although I don't have any I/O devices implemented, which is a bit hard in logisim, so I left them out. But to get a better understanding of the data path, I stripped away all the control logic so that we can give the control signals manually and just play with the data path and see what happens. So this is what you see here. So let's take a look at what we have. We have the 3 data registers, Mbr, AC, and LR, and these are 18 bits wide. Mbr is the memory buffer register, and it holds the value that has been read from memory, and it is to be stored back into memory. LR is the live register, and it's connected to the flexo writer. So whenever a key is struck on the flexo writer, it will set the highest bit in LR and also send the character value. And also LR can be used as a temporary register. And AC is the accumulator, which is where we do arithmetic together with MB. Then we have the 16-bit address registers, PC and MAR. MAR is the memory address register, and it selects one word in core memory that is to be accessed. And PC is the program counter, which always holds the address of the instruction following the instruction that is currently being executed. And we have the instruction register, IR, that holds the opcode for the current instruction. And this is then decoded by the control logic to drive the whole machine. So let's take a look maybe how a memory cycle is done. Since this is a core memory, which is an analog process to use, of course, I had to simulate this with a RAM block in logisim. This is not perfect, of course, but it's the best I could do. So we have some address in MAR to address some location in memory, and we want to read this into Mbr now. So the first step will be to clear Mbr because it currently still holds a value, and this is what this signal does, Mbr clear. Now it's 0. The next step is that we will write a 0 into the word that we want to read, because to read core memory you write a 0 and then the bits that get flipped induce a current in a wire that you can sense and then strobe into Mbr. Now this I had to simulate, of course, and I simulated this with a temporary register here, the strobe amplifier, sense amplifier register. So let's do this. We set the read flip-flop, and this will clear this core location and send it into the sense amplifier instead. Boom. And next we clear one of the two flip-flops, which ends the read operation. And next we can strobe this value into the Mbr. This is sense amplifier strobe. And now we have this value in Mbr. And the upper bit you see here is just the parity bit, which has also been read into what could still be considered Mbr, and it corresponds to this light green wire here. But now, of course, we have a 0 in this location, and we want to write back the original value. So we do a write cycle. And this is done by first setting the inhibit flip-flop. Now it is set, and then clearing the other read flip-flop. Now we have the value back in memory. And then we clear the inhibit flip-flop, and this concludes the memory cycle. So we have now written a value. We have read a value from memory into Mbr. And to write a value, we would just ignore the sense amplifiers. We wouldn't strobe them into Mbr. So let's do something with this value now. We currently have some value in the accumulator, and maybe we want to add this value in Mbr to the accumulator. And this is done in two steps. The first step is forming the half sum, which is an exclusive OR, and this is done with the add signal. So now we have the exclusive OR of these two. And the next step is inserting the carry bits. And for that I have to enable the carry. And this is another hack I had to implement because I don't know how the carry chain is actually realized in the actual machine. And then we send the carry pulse. And now we have the sum of AC and Mbr in the accumulator. Now let's look at a few other pulses that we can give. For instance, we can complement the accumulator with the AC-com signal, and we can clear, say, the left half of the accumulator, and we can write, cycle, or shift the accumulator as well. So first maybe let's cycle it. And now that we have a sign bit in the leftmost bit, let's do an arithmetic shift and see that it is copied, that it is shifted right. And then complementing again, maybe. So this is what you can do with the accumulator. Maybe let's complement it back and now read the test switches for the accumulator into it. And this is just an OR. So now we have the 252 in the lower in the accumulator as well. The same can be done with MBR. So let's load TBR into MBR. And you can see that we have the OR of what was previously there and our switch register. And now we see a signal here because the value that we want to write to core memory should have odd parity, but this value now, together with a parity bit, has even parity. So there is a signal correct parity which will flip the parity bit and thus correcting parity. Now something we can do with LR is put MBR into it, for instance. And then when we clear MBR, we can put LR back into MBR. And I think that concludes the discussion of the data section here. Now let's look at the address section. When we read an instruction from memory, the instruction portion is transferred to the instruction register, and the address portion is transferred to the address register. So let's see what we can do with those. Actually, let's start with this, transferring MBR to MAR. So this would move then 140045 into MAR, and you can see that here. Now this would address just some random value in memory, but we can move this value incremented by 1 into the program counter. So for that we have to clear it first and then do the PC count signal. And now this is 1 more than this. And we can repeat that, move the PC into Mar and clear, count, and that way we're counting up so that we can execute instructions in sequence later on. The instruction register just there is only one interesting signal really, MBR to IR, and this will move the uppermost bits in MBR into the instruction register. We also have the test switch storage, and this is just 16 rows of 18-bit switches of 18 switches that can be read into MBR instead of memory, but I'm not going to go into this really now. It's not so interesting. This was probably mainly used for initial bring up and debugging of the machine, but it could also be used for small bootstrap, for instance, or for holding constants that you don't want to accidentally overwrite. Okay, so that concludes the first part of this TX-0 explanation. Thanks for watching.